What if everything you see when you look up at the night sky, every glimmer of starlight, every swirl of a distant galaxy, every atom in your own body, all traces back to a single, absurdly simple particle that was forged in a 3-minute window right after the universe was born? That particle is hydrogen, element number 1 on the periodic table. And it is not merely the lightest atom in existence, it is the architect of everything. Roughly 75% of all ordinary matter in the cosmos is hydrogen. It is the fuel that lights the stars, the glue that holds DNA together, the medium through which life itself became possible, and quite possibly the energy source that will power the cities of the future. The story of hydrogen is the story of the universe, and when you understand why, you will never look at a glass of water, a beam of sunlight, or a clear night sky the same way again. The universe began approximately 13.8 billion years ago in an event physicists call the Big Bang. In the first fractions of a second, reality as we know it did not yet exist. There were no atoms, no molecules, no stars, and certainly no planets. There was only an inconceivably hot, dense fireball of energy expanding at a furious pace. Within the first microsecond, fundamental particles called quarks condensed out of the primordial soup, and those quarks quickly combined in groups of 3 to form protons and neutrons. A proton, standing alone, is already the nucleus of a hydrogen atom. So in a very real sense, the identity of hydrogen was encoded into the universe from nearly the first heartbeat of time. But the critical drama unfolded in a narrow window between roughly 3 and 20 minutes after the Big Bang, a period cosmologists call Big Bang nucleosynthesis. During this window, the temperature of the expanding fireball dropped to about 1 billion degrees Kelvin, which is roughly 60 times hotter than the core of our sun, but cool enough for protons and neutrons to begin sticking together through the strong nuclear force. Protons collided with neutrons to form deuterium, a heavier version of hydrogen that contains 1 proton and 1 neutron in its nucleus instead of just a lone proton. Deuterium nuclei then collided with each other and with additional protons and neutrons to build helium-3 nuclei, which contain 2 protons and 1 neutron, and helium-4 nuclei. The ordinary helium we fill balloons with, containing 2 protons and 2 neutrons. Trace amounts of lithium-7 were also produced, but nothing heavier. The reason the process stalled is one of the most important facts in all of astrophysics. There are no stable nuclei with a mass number of 5 or 8. This is known as the mass 5 and mass 8 gap, because no stable nucleus exists at those mass numbers. There is no easy stepping stone from helium-4 to carbon-12 or any heavier element. The only way to jump the gap is through a simultaneous 3-body collision, where 3 helium-4 nuclei slam together at the same instant to form carbon-12, a process called the triple alpha reaction. But in the rapidly expanding and cooling early universe, densities dropped too fast for 3-body collisions to happen at any meaningful rate. So nucleosynthesis simply stopped. The result was a cosmos composed almost entirely of hydrogen and helium, with hydrogen making up about 75% of all baryonic mass and helium accounting for about 24%, and everything else, lithium, beryllium, and all heavier elements combined, totaling less than 1%. This ratio was essentially locked in during those first 20 minutes and has remained the baseline composition of the universe ever since. Every subsequent chapter of cosmic history, from the birth of the first star to the evolution of life on a small rocky planet orbiting a modest yellow star, flows from this initial condition. Why hydrogen ended up so dominant is not just a quirk of timing. It is a consequence of the fundamental constants of nature being tuned in a very particular way. The strong nuclear force, which binds protons and neutrons together inside a nucleus, has a specific strength. If that strength were slightly greater, protons would have fused together so readily during Big Bang nucleosynthesis that almost all hydrogen would have been consumed, leaving a universe dominated by helium or heavier elements. In such a cosmos, the raw material for long-lived stars like our sun would have been scarce, and the gentle, sustained nuclear burning that gives a star a lifespan of billions of years would have been impossible. If the strong force were slightly weaker, deuterium would have been unstable, meaning the very first rung of the nucleosynthetic ladder would have been missing, and no helium would have formed at all. The universe would have been pure hydrogen, which might sound like an advantage until you realize that without any heavier seed elements, the chemistry of star formation and later element production would have been profoundly altered. The electromagnetic force also plays a role. Its strength determines how tightly electrons are bound to nuclei, which in turn affects how atoms interact, how light is emitted and absorbed, and ultimately how chemistry works. The ratio of electromagnetic to strong force strength is part of what makes the mass 5 and mass 8 gaps exist in the first place. Change these constants by even a few percent, and you get a radically different periodic table, or possibly no stable atoms at all. So the fact that we live in a universe where hydrogen is overwhelmingly abundant is not accidental. Hindi ang trivial sensa. It is the product of physical law, and that law appears to be exquisitely calibrated to produce exactly this outcome. After nucleosynthesis ended, the universe continued to expand and cool for hundreds of thousands of years. During this epoch, the cosmos was a hot plasma of hydrogen and helium nuclei mixed with free electrons and photons. Light could not travel far because it kept scattering off the free electrons. So the universe was essentially opaque, like the inside of a dense fog. Then about 380,000 years after the Big Bang, the temperature dropped below roughly 3,000 Kelvin. And something pivotal happened. Electrons finally had little enough energy to be captured by hydrogen nuclei, forming neutral hydrogen atoms. This event is called recombination, and it was the moment the universe became transparent. Photons were suddenly free to stream across space without being scattered, and that ancient light is still detectable today as the cosmic microwave background radiation, a faint glow that fills the entire sky and serves as a snapshot of the universe when it was less than 400,000 years old. After recombination, the universe entered a period sometimes called the cosmic dark ages. There were no stars, no galaxies, and no sources of light other than the fading afterglow of the Big Bang. The cosmos was filled with neutral hydrogen gas, along with helium, drifting through an expanding void governed by gravity. But gravity, even at its most gentle, is relentless. Tiny density fluctuations that had been imprinted in the early universe. Small regions where matter was slightly denser than average began to grow. Dark matter, the mysterious substance that makes up about 83% of all gravitational mass in the universe, but does not interact with light, played a crucial role here. Dark matter clumps formed first because dark matter does not experience the radiation pressure that kept ordinary matter smoothed out during the plasma era. These dark matter halos became gravitational cradles, pulling ordinary hydrogen and helium gas into their centers. Over tens of millions of years, the gas accumulated in these halos, growing denser and denser. A critical step in the process of forming the first stars was cooling. For a cloud of gas to collapse under its own gravity and form a star, it needs to radiate away its thermal energy, otherwise, the pressure of the hot gas resists gravitational compression, and the cloud simply bounces back to equilibrium. In the modern universe, this cooling is accomplished efficiently by atoms and molecules of carbon, oxygen, nitrogen, and other heavy elements, which have many energy levels and can emit radiation across a wide range of wavelengths. But in the primordial universe, there were no heavy elements. The only coolants available were hydrogen and helium atoms and, crucially, molecular hydrogen, H2. When two hydrogen atoms bond together to form an H2 molecule, that molecule can rotate and vibrate in quantized ways, and transitions between those rotational and vibrational states emit infrared photons that carry energy away from the gas cloud. Molecular hydrogen is not a very efficient coolant compared to carbon monoxide or ionized carbon, which dominate cooling in modern galaxies, but it was the best the early universe had. Without H2, the first gas clouds could not have cooled below a few thousand degrees, and stars would have taken far longer to form, if they formed at all. With H2, clouds could cool to a few hundred degrees, allowing them to collapse to the densities needed to ignite nuclear fusion. This is one of the most underappreciated facts in all of cosmology. Molecular hydrogen was the midwife of the first generation of stars. The very element that dominated the universe also provided the mechanism by which that dominance could be converted into structure. The first stars, often called population 3 stars by astronomers, are believed to have formed roughly 100 to 200 million years after the Big Bang. No population 3 star has ever been directly observed because they all burned out long ago. But theoretical models and computer simulations give us a remarkably detailed picture of what they must have been like. Because the primordial gas had no heavy elements, the cooling was less efficient than in modern star-forming regions, and the gas clouds that collapsed were more massive. As a result, many population 3 stars are thought to have been enormous, possibly tens to hundreds of times the mass of our Sun. Massive stars burn their fuel profligately. A star with 100 solar masses might exhaust its hydrogen fuel in just a few million years, compared to the 10 billion year lifespan of a star like our Sun. These first giant stars blazed with extraordinary luminosity, ionizing the surrounding hydrogen gas with their intense ultraviolet radiation and ending the cosmic dark ages in a process called reionization. The appearance of these first stars was the universe switching the lights on, and the power source was hydrogen fusion. Inside every star, including our own Sun, hydrogen serves as the primary fuel for nuclear fusion. The dominant process in stars like the Sun is called the proton-proton chain. In this reaction sequence, two protons, which are simply hydrogen nuclei, collide and fuse. One of the protons converts into a neutron via the weak nuclear force, releasing a positron and a neutrino, and the result is a deuterium nucleus. The deuterium nucleus then captures another proton to form helium-3, and two helium-3 nuclei fuse to produce one helium-4 nucleus plus two free protons that can go on to repeat the cycle. The net result of the entire chain is that 4 protons are converted into one helium-4 nucleus, 2 positrons, 2 neutrinos, and a burst of energy in the form of gamma-ray photons. The energy comes from the fact that a helium-4 nucleus has slightly less mass than 4 individual protons. The missing mass, about 0.7% of the original mass of the 4 protons, has been converted into energy according to Albert Einstein's famous equation E equals mc squared. That 0.7% may sound trivial, but when multiplied by the astronomical quantity of hydrogen in a star, it adds up to a staggering amount of power. Our Sun fuses approximately 600 million tons of hydrogen into helium every single second. In doing so, about 4 million tons of mass are converted into pure energy each second. Energy that radiates outward as sunlight and keeps our planet warm enough for liquid water and life. The Sun has been doing this for about 4.6 billion years and has enough hydrogen fuel left to continue for roughly another 5 billion years. This is what makes hydrogen so extraordinary as a stellar fuel. It provides a vast, long-duration energy source that can sustain a star for billions of years, giving planets orbiting that star ample time for complex chemistry and biological evolution to unfold. More massive stars than the Sun use a different fusion pathway called the CNO cycle, named for carbon, nitrogen, and oxygen, which act as catalysts in the reaction. The net result is the same. 4 protons become one helium-4 nucleus with the release of energy. But the CNO cycle operates at higher temperatures and is much more sensitive to temperature changes, which is why it dominates in stars larger than about 1.3 solar masses, where core temperatures exceed roughly 17 million Kelvin. Regardless of the specific pathway, the fundamental story is the same. Hydrogen is being converted into helium, and the mass difference is released as energy. This is the engine that drives every star in the observable universe. From tiny red dwarfs that will burn for trillions of years to supergiant blue stars that exhaust their fuel in a few million years and explode in spectacular supernovae. When a massive star, typically more than about 8 times the mass of the Sun, runs out of hydrogen in its core, it does not simply die. Instead, it enters a series of increasingly desperate fusion stages. The core contracts and heats up until helium nuclei begin fusing into carbon through the triple alpha process. When the helium runs out, the core contracts further and carbon begins fusing into neon. Then neon into oxygen, oxygen into silicon, and silicon into iron. Each successive fuel lasts for a shorter time. Hydrogen burning may last millions of years, helium burning lasts hundreds of thousands of years. Carbon burning lasts a few hundred years, neon burning lasts about a year. Oxygen burning lasts a few months, and silicon burning lasts only about a day. The reason the chain stops at iron is that iron 56 has the highest binding energy per nucleon of any element. Fusing iron does not release energy, it costs energy. So once the core is solid iron, there is no more fuel to burn, and the core collapses under its own gravity in a fraction of a second. The outer layers of the star come crashing down onto the incompressible core and bounce off in a cataclysmic explosion called a core collapse supernova. In that explosion, temperatures and neutron fluxes are so extreme that elements heavier than iron, including gold, platinum, uranium, and all the rest, are forged through rapid neutron capture processes. The explosion flings these newly minted heavy elements into interstellar space, where they mix with existing hydrogen and helium gas to enrich the raw material for future generations of stars. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood, was forged in the interior of a star that lived and died before our sun was born. And the fuel that powered that star through every stage of its life, the fuel that initiated the entire cascade of element production, was hydrogen. The periodic table is, in a very real sense, hydrogen's family tree. Now let us shift from the cosmic to the quantum scale, because the story of hydrogen at the level of individual atoms is just as profound. The hydrogen atom, consisting of a single proton orbited by a single electron, is the simplest atom in existence, and this simplicity made it the Rosetta Stone of modern physics. In 1913, the Danish physicist Niels Bohr proposed a revolutionary model of the atom to explain the mysterious spectral lines of hydrogen. When hydrogen gas is heated or energized, it emits light only at specific wavelengths, producing a pattern of colored lines called an emission spectrum. The Swiss mathematician Johann Balmer had discovered a mathematical formula for the visible lines of hydrogen's spectrum in 1885, but nobody understood why the formula worked. Bohr's insight was that the electron in a hydrogen atom can only occupy certain discrete energy levels, or orbits, around the nucleus. When the electron jumps from a higher energy level to a lower one, it emits a photon whose energy, and therefore wavelength, corresponds exactly to the energy difference between the two levels. This was a radical break from classical physics, which said the electron should be able to orbit at any distance and radiate energy continuously, spiraling into the nucleus in a tiny fraction of a second. Bohr's quantization condition, the idea that only certain orbits are allowed, saved the atom from collapse and explained hydrogen's spectral lines with stunning accuracy. The radius of the lowest energy orbit in Bohr's model, called the Bohr radius, is approximately 0.529 angstroms, or about 53 picometers. This is the characteristic size of a hydrogen atom and one of the most fundamental length scales in all of physics. Bohr's model was a landmark, but it was only the beginning. In the 1920s, Werner Heisenberg, Erwin Schrödinger, Max Born, Paul Dirac, and others developed the full mathematical framework of quantum mechanics, and once again, hydrogen was the testing ground. Schrödinger's wave equation, when applied to the hydrogen atom, can be solved exactly, yielding a complete set of wave functions called orbitals that describe the probability distribution of the electron around the nucleus. The hydrogen atom is, in fact, the only atom for which the Schrödinger equation can be solved analytically without approximations. Every other atom, from helium with its 2 electrons to uranium with its 92, requires approximation methods. But the solutions for hydrogen, the 1s orbital, the 2s and 2p orbitals, the 3s, 3p and 3d orbitals, and so on, established the conceptual framework that physicists and chemists use to understand every atom in the periodic table. The shapes and energies of these hydrogen orbitals are taught in every introductory chemistry and physics course in every university in America and around the world, and they form the basis for understanding chemical bonding, molecular structure, and the properties of matter. The precision with which hydrogen spectrum can be measured and predicted has made it an indispensable tool for testing the most fundamental theories of physics. Quantum electrodynamics, or QED, the theory that describes how light and matter interact at the quantum level, makes predictions about the energy levels of hydrogen that agree with experiment to better than 1 part in a trillion. This is one of the most precisely verified predictions in all of science. Small deviations in hydrogen's energy levels, such as the Lamb shift discovered by American physicist Willis Lamb in 1947, drove the development of QED and earned Lamb the Nobel Prize in Physics. The hyperfine structure of hydrogen, a tiny splitting of energy levels caused by the interaction between the magnetic moments of the proton and the electron, produces the famous 21-centimeter radio emission line. This spectral line has become one of the most important tools in radio astronomy, allowing scientists to map the distribution of neutral hydrogen gas throughout galaxies and across the cosmos. The 21-centimeter line was first detected in 1951, and it has since been used to map the spiral structure of our Milky Way galaxy, measure the rotation curves of distant galaxies, and probe the distribution of matter in the early universe. Hydrogen's spectral fingerprint is literally how we read the structure of the cosmos. Experiments with antihydrogen, the antimatter counterpart of hydrogen consisting of an antiproton orbited by a positron, have been conducted at CERN, the European Particle Physics Laboratory in Geneva, to test one of the most fundamental symmetries in physics, CPT symmetry, which states that the laws of physics should remain unchanged if you simultaneously reverse charge, mirror spatial coordinates, and reverse the flow of time. If CPT symmetry is exact, then antihydrogen should have exactly the same spectrum as ordinary hydrogen. Experiments by the Alpha Collaboration at CERN have confirmed this to increasingly high precision, placing tight constraints on any possible violation of CPT symmetry. Once again, hydrogen and its antimatter twin stands at the frontier of fundamental physics. Moving from physics to chemistry, hydrogen's role becomes even more sweeping. Hydrogen is unique among elements because it sits at the top of the periodic table with just 1 electron and 1 proton, giving it extraordinary versatility in chemical bonding. It can lose its single electron to become a bare proton, the hydrogen ion H+, which is essentially just a proton and the smallest possible ion. It can share its electron in a covalent bond, as it does in the hydrogen molecule H2 or in water. H2O. It can even, in rare circumstances, gain an electron to become the hydride ion H-. But perhaps hydrogen's most consequential chemical trick is the hydrogen bond, a type of weak attractive force that arises when a hydrogen atom covalently bonded to a highly electronegative atom like oxygen, nitrogen, or fluorine is attracted to a lone pair of electrons on another electronegative atom in a neighboring molecule. The hydrogen bond is not a true chemical bond in the conventional sense. It is roughly 10 to 20 times weaker than a covalent bond. But its influence on the properties of matter is out of all proportion to its strength. Water is the most familiar example. A single water molecule consists of 1 oxygen atom covalently bonded to 2 hydrogen atoms, arranged at an angle of about 104.5 degrees. The oxygen atom is far more electronegative than hydrogen, meaning it pulls the shared electrons toward itself, giving the oxygen end of the molecule a partial negative charge and the hydrogen end's partial positive charges. This makes water a polar molecule, and the partially positive hydrogen atoms of one water molecule are attracted to the partially negative oxygen atoms of neighboring water molecules. These intermolecular hydrogen bonds are what give water its remarkably high boiling point of 212 degrees Fahrenheit at standard pressure. Without hydrogen bonds, water would boil at roughly negative 140 degrees Fahrenheit, similar to hydrogen sulfide, H2S, which has a comparable molecular weight but forms much weaker intermolecular interactions. At room temperature, water would be a gas, not a liquid, and Earth would be a dry, lifeless rock. Hydrogen bonds are also responsible for water's exceptionally high specific heat capacity, meaning water can absorb large amounts of thermal energy before its temperature rises significantly. This property is critical for climate regulation. The oceans absorb vast quantities of solar energy and release it slowly, moderating temperature extremes between day and night and between seasons. Without this thermal buffering, Earth's surface temperature would swing wildly. making complex life nearly impossible. Another consequence of hydrogen bonding is the anomalous density behavior of water as it freezes. Most liquids become denser as they cool and solidify, but water reaches maximum density at about 39 degrees Fahrenheit and then becomes less dense as it cools further to the freezing point at 32 degrees Fahrenheit. This is because when water freezes, the hydrogen bonds lock the molecules into an open hexagonal crystal lattice that occupies more volume than the disordered liquid. As a result, ice floats on water. This seemingly simple fact has profound biological implications. When a lake freezes in winter, the ice forms a layer on top that insulates the liquid water beneath, allowing fish, amphibians, and aquatic microorganisms to survive through the cold months. If ice sank, lakes and eventually oceans would freeze from the bottom up, killing aquatic life and potentially triggering runaway glaciation that could make Earth permanently inhospitable. The importance of hydrogen bonds extends far beyond the physics of water. In biology, hydrogen bonds are the invisible scaffolding that holds life's most essential molecules together. Consider DNA, the molecule that encodes the genetic instructions for building and maintaining every living organism. DNA consists of two long strands of nucleotides wound around each other in the iconic double helix structure first described by James Watson and Francis Crick in 1953. Building on the X-ray crystallography work of Rosalind Franklin, the two strands are held together by hydrogen bonds between complementary base pairs. Adenine pairs with thymine through 2 hydrogen bonds, and guanine pairs with cytosine through 3 hydrogen bonds. This specific, selective pairing is what makes DNA replication possible. When a cell divides, enzymes unzip the 2 strands by breaking the hydrogen bonds between the base pairs. Each strand then serves as a template for building a new complementary strand, and the hydrogen bonds reform to seal the new double helix. The beauty of this system is that hydrogen bonds are strong enough to hold the 2 strands together under normal conditions, maintaining the integrity of the genetic code, but weak enough to be broken by the cellular machinery when replication or gene expression needs to occur. If the bonds were any stronger, the strands could not be separated, and DNA could never be copied or read. If they were any weaker, the double helix would fall apart spontaneously, and genetic information would be lost. Hydrogen bonds hit a perfect sweet spot of stability and accessibility, and this is not a coincidence. It is a reflection of the unique chemical properties of hydrogen as an element. Proteins, the molecular machines that carry out almost every function in a living cell, also depend critically on hydrogen bonds for their structure. A protein is a long chain of amino acids, and the sequence of those amino acids is determined by the DNA code. But a protein's function depends not just on its sequence, but on its 3-dimensional shape, the way the chain folds up in space. 2 of the most common structural motifs in proteins, the alpha helix and the beta sheet, are stabilized by hydrogen bonds between the backbone carbonyl, C=O, groups and amide, NH, groups of the amino acid chain. In an alpha helix, each carbonyl oxygen forms a hydrogen bond with the amide hydrogen of the amino acid 4 residues ahead in the chain, creating a coiled, spring-like structure. In a beta sheet, hydrogen bonds form between adjacent segments of the polypeptide chain that run either parallel or antiparallel to each other, creating a flat, rigid sheet. Without these hydrogen bonds, proteins could not fold into their functional shapes. Enzymes could not catalyze biochemical reactions, antibodies could not recognize pathogens, and the entire molecular machinery of life would cease to function. It is not an overstatement to say that without hydrogen bonds, life as we know it on Earth would be impossible. Now let us zoom back out to the largest scales and consider how hydrogen shapes the architecture of the cosmos. The universe is not a uniform sea of matter. Instead, matter is organized into a vast web-like structure sometimes called the cosmic web. Galaxies are not scattered randomly through space. They are arranged along filaments and sheets surrounding enormous empty voids. This structure was seeded by tiny density fluctuations in the early universe that grew over billions of years under the influence of gravity. Dark matter, which outmasses ordinary matter by about 5 to 1, formed the initial scaffolding of the cosmic web. Dark matter halos collapsed first, and ordinary matter, overwhelmingly hydrogen and helium gas, fell into these halos and accumulated. Within these halos, the gas cooled, fragmented, and formed stars, which gathered into galaxies. The galaxies themselves clustered along the filaments of the dark matter web, creating the large-scale structure we observe today. If dark matter is the skeleton of the cosmos, hydrogen is the flesh. Without hydrogen to provide the raw material for stars and the cooling mechanisms for gas collapse, the dark matter scaffolding would have remained invisible and inert, a skeleton with no body. Within individual galaxies, hydrogen governs the rate and distribution of star formation. In spiral galaxies like our Milky Way, most of the cold, dense gas from which new stars form is concentrated in the spiral arms. This gas is predominantly molecular hydrogen, H2, mixed with small amounts of heavier molecules and dust. Giant molecular clouds, some containing hundreds of thousands of solar masses of gas, are the nurseries where new stars are born. The Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is one such star-forming region, where hundreds of young stars are emerging from a massive cloud of hydrogen gas. The rate at which a galaxy forms new stars is directly tied to its reservoir of cold hydrogen gas. Galaxies that have used up their gas supply, or had it stripped away by interactions with other galaxies, or heated by the energy output of a supermassive black hole at their center, stop forming new stars and gradually age and redden as their existing stellar population evolves. Elliptical galaxies, which are gas-poor, have very little ongoing star formation, while gas-rich irregular and spiral galaxies continue to produce new stars. The entire evolutionary trajectory of a galaxy, whether it remains actively star-forming or transitions into a quiescent, red and dead state, is largely determined by its hydrogen budget. The flow of hydrogen gas also plays a role in feeding the supermassive black holes that reside at the centers of most galaxies. When gas falls toward a black hole, it forms a swirling accretion disk that heats up to millions of degrees, producing intense radiation across the electromagnetic spectrum, from radio waves to X-rays. When the accretion rate is high enough, the galaxy's center lights up as an active galactic nucleus, or AGN, and in the most extreme cases, a quasar, which can outshine the entire host galaxy by a factor of 100. The energy output of an AGN or quasar can drive powerful winds and jets that blow hydrogen gas out of the galaxy, shutting down star formation across the entire system. This feedback loop between black hole growth and galaxy evolution is one of the most active areas of research in astrophysics, and at its heart is the cycle of hydrogen gas flowing in, being consumed or expelled, and determining the fate of the galaxy. On the scale of individual star systems, hydrogen determines the architecture of planetary systems. When a cloud of hydrogen gas collapses to form a star, it typically forms a rotating disk of gas and dust around the young star, called a protoplanetary disk. Within this disk, dust grains collide and stick together, gradually building up larger and larger bodies, from pebbles to boulders to planetesimals to protoplanets. The composition of the planets that form depends on where in the disk they coalesce. Close to the star, where temperatures are high, only rocky and metallic materials can survive as solids, giving rise to terrestrial planets like Mercury, Venus, Earth, and Mars. Farther out, beyond the so-called snow line where water ice can form, much more solid material is available, and protoplanets can grow large enough to gravitationally capture vast envelopes of hydrogen and helium gas from the disk, becoming gas giant planets like Jupiter and Saturn. Jupiter, the largest planet in our solar system, is about 90% hydrogen by number of atoms. Saturn is similar. These worlds are essentially failed stars, bodies that accumulated enormous quantities of hydrogen but never reached the mass threshold of about 80 Jupiter masses needed to ignite hydrogen fusion in their cores. Even the ice giant planets, Uranus and Neptune, contain substantial amounts of hydrogen, both in their atmospheres and locked in chemical compounds in their interiors. Earth itself, though a rocky planet, owes much of its character to hydrogen. Earth's water, essential for all life, is 2/3 hydrogen by number of atoms. The hydrogen in Earth's water likely arrived via comets and water-rich asteroids that bombarded the young Earth during its first few 100 million years, delivering volatile materials from the outer reaches of the solar system. Hydrogen is also a key component of the organic molecules that form the basis of biochemistry. Carbohydrates, lipids, proteins, and nucleic acids all contain hydrogen in abundance. The very first self-replicating molecules that arose in Earth's primordial oceans, whatever they were certainly hydrogen-containing compounds. And the metabolic pathways that evolved to sustain the earliest life forms involved chemical reactions with hydrogen at their core. Some of the oldest known microorganisms on Earth, the methanogens, derive energy by combining hydrogen and carbon dioxide to produce methane. These organisms may represent an echo of life's earliest chemistry, dating back nearly 4 billion years. Understanding how deeply hydrogen is woven into the fabric of existence naturally leads to the question of whether we can harness its power for our own civilization. Humanity has been using hydrogen indirectly since we first lit a fire, because burning hydrocarbons, whether wood, coal, oil, or natural gas, involves breaking carbon-hydrogen bonds and combining the hydrogen with oxygen to release energy and form water. But the dream of using hydrogen directly, cleanly, and efficiently as an energy carrier has captivated scientists and engineers for decades, and it is closer to reality than it has ever been. There are two main approaches: hydrogen as a fuel for fuel cells and combustion engines, and hydrogen as a fuel for nuclear fusion. Both have the potential to transform civilization, and both face significant challenges. Fuel cells convert hydrogen directly into electricity through an electrochemical reaction. In a proton exchange membrane fuel cell, hydrogen gas enters one side of the cell and is split into protons and electrons by a platinum catalyst. The protons pass through a polymer membrane to the other side, while the electrons are forced to travel through an external circuit, generating electricity. On the other side, the protons, electrons, and oxygen from the air combine to form water, which is the only byproduct. No carbon dioxide, no particulates, no sulfur dioxide, just pure water. Fuel cell vehicles have been commercially available for several years. Toyota's Mirai and Hyundai's Nexo are examples of hydrogen fuel cell cars that can be purchased in the United States, with a range of about 300 to 400 miles on a single tank and a refueling time of about 5 minutes, comparable to a conventional gasoline car. But the hydrogen fuel cell economy faces substantial obstacles. The biggest is the cost and carbon footprint of hydrogen production. About 95% of the hydrogen produced in the United States today is made by a process called steam methane reforming, in which natural gas reacts with steam at high temperatures to produce hydrogen and carbon dioxide. This so-called gray hydrogen is relatively inexpensive, currently around $1 to $2 per kilogram, but it generates significant greenhouse gas emissions, roughly 10 kilograms of CO2 for every kilogram of hydrogen produced. To be truly clean, hydrogen must be produced by electrolysis, splitting water into hydrogen and oxygen using electricity from renewable sources like wind or solar. This green hydrogen currently costs between $3.50 and $6 per kilogram, according to multiple industry analyses from 2024, though projections suggest costs could fall to under $2 per kilogram by 2030 as renewable electricity prices continue to drop and electrolyzer technology improves. The United States government has committed over $9 billion through the Bipartisan Infrastructure Law to support clean hydrogen initiatives, including regional hydrogen hubs designed to create integrated production, distribution, and consumption networks. The Inflation Reduction Act provides additional tax credits of up to $3 per kilogram for clean hydrogen production, further closing the cost gap with fossil-derived hydrogen. Beyond production cost, hydrogen faces challenges in storage and transportation. Hydrogen has the highest energy per unit mass of any chemical fuel, about 120 megajoules per kilogram, nearly 3 times that of gasoline. But it has extremely low energy per unit volume, because it is such a light gas. At standard temperature and pressure, a kilogram of hydrogen occupies about 11 cubic meters, roughly the volume of a large bedroom. To make hydrogen practical as a transportation fuel, it must be compressed to about 10 0.000 pounds per square inch, nearly 700 atmospheres, or liquefied at minus 423 degrees Fahrenheit, minus 253 degrees Celsius. Both approaches require significant energy input and specialized equipment. High-pressure hydrogen tanks for vehicles are made of advanced carbon fiber composites and are extremely expensive. Liquid hydrogen storage requires heavily insulated cryogenic vessels and suffers from boil-off losses, as some hydrogen inevitably evaporates over time. Transporting hydrogen through existing natural gas pipelines is theoretically possible, but hydrogen causes embrittlement in many steel alloys, gradually weakening pipe walls and increasing the risk of leaks and failures. New pipelines designed specifically for hydrogen, or the development of embrittlement-resistant materials, would be needed for large-scale hydrogen distribution. The refueling infrastructure for hydrogen vehicles is still sparse. As of early 2025, there were fewer than 100 public hydrogen fueling stations in the entire United States, almost all of them in California. The other great hydrogen energy dream, and arguably the more transformative one, is nuclear fusion. If we can learn to fuse hydrogen isotopes the way the sun does, we could unlock a virtually limitless supply of clean energy. The fuel for the most promising fusion reactions is a mixture of deuterium, hydrogen with 1 neutron, and tritium, hydrogen with 2 neutrons. Deuterium is naturally abundant. It makes up about 1 in every 6 for 100 hydrogen atoms in ordinary water, meaning the world's oceans contain enough deuterium to power civilization for billions of years. Tritium is radioactive and scarce in nature, with a half-life of only about 12.3 years. But it can be produced by bombarding lithium with neutrons, and lithium is relatively abundant in Earth's crust and oceans. When a deuterium nucleus and a tritium nucleus fuse, they produce a helium-4 nucleus, a high-energy neutron, and 17.6 million electron volts of energy, roughly 10 million times more energy per reaction than a typical chemical reaction. 1 gram of deuterium-tritium fuel releases as much energy as burning about 11 tons of coal. The challenge is creating the conditions for fusion to occur. The deuterium and tritium nuclei are both positively charged, so they repel each other electrostatically. To overcome this repulsion and allow the strong nuclear force to pull them together, the fuel must be heated to temperatures exceeding 100 million Kelvin, far hotter than the core of the sun, and confined at sufficient density for long enough that a meaningful number of fusion reactions occur. 2 main approaches have been pursued for decades. The first is magnetic confinement fusion, exemplified by the tokamak reactor design. A tokamak uses powerful magnetic fields to confine a plasma of deuterium and tritium in a donut-shaped chamber, squeezing and heating it until fusion occurs. The most ambitious magnetic confinement project in the world is ITER, which stands for International Thermonuclear Experimental Reactor, currently under construction in southern France. ITER is a collaboration among the United States, the European Union, Russia, China, Japan, South Korea, and India. When completed, ITER aims to produce 500 megawatts of fusion power from an input of just 50 megawatts of heating power, a 10-fold energy gain designated Q equals 10. However, ITER has faced repeated delays and cost overruns. The original first plasma date was 2020, but successive revisions have pushed this to 2034 or later. Full deuterium-tritium operations are not expected until the late 2030s at the earliest. The total cost of the project is estimated at well over $25 billion. The second approach is inertial confinement fusion, in which tiny pellets of deuterium-tritium fuel are compressed and heated by intense laser beams or other energy drivers. The National Ignition Facility, or NIF, at Lawrence Livermore National Laboratory in California, is the world's most powerful laser system, with 192 laser beams that can deliver over 2 megajoules of ultraviolet light energy to a target the size of a pencil eraser. On December 5, 2022, NIF achieved a historic milestone for the first time. A fusion reaction produced more energy than the laser energy delivered to the target. The lasers delivered 2.05 megajoules, and the fusion reaction produced 3.15 megajoules, a target gain of about 1.5. This was scientific break-even. and it made headlines around the world as proof that net energy gain from fusion was physically achievable. NIF has since improved on this result. On February 10, 2024, NIF produced 5.2 megajoules of fusion energy from a 2.2 megajoule laser shot, achieving a target gain of about 2.3. And in April 2025, NIF set yet another record with a fusion yield of 8.6 megajoules and a target gain exceeding 4. These results represent breathtaking progress. But it is important to note that the 192 NIF lasers themselves consume far more electrical energy than they deliver to the target. The wall plug efficiency of the laser system is only about 1%. So while the fusion target produces more energy than it absorbs from the lasers, the overall system is still nowhere near break-even from an engineering perspective. Turning laser fusion into a practical power source will require lasers that are far more efficient, that can fire many times per second rather than a few times per day, and targets that can be manufactured cheaply in the millions. These are enormous engineering challenges, but the physics has been proven, and that is the indispensable first step. Private fusion companies have also entered the race, backed by billions of dollars in venture capital. Companies like Commonwealth Fusion Systems, TE Technologies, Helion Energy, and others are pursuing innovative approaches to fusion that aim to reach commercial viability faster than the government-funded megaprojects. Commonwealth Fusion Systems, a spin-off from the Massachusetts Institute of Technology, is developing a compact tokamak called Spark that uses high-temperature superconducting magnets to achieve much stronger magnetic fields in a smaller device. Helion Energy is pursuing a field-reversed configuration approach and has signed a power purchase agreement with Microsoft to supply fusion electricity, the first such agreement in history. Whether any of these efforts will succeed on their ambitious timelines remains to be seen. But the sheer volume of investment and innovation in the field is unprecedented. If fusion power becomes a reality, its impact on human civilization would be difficult to overstate. A single fusion power plant could generate electricity for millions of homes using fuel derived from seawater, with no greenhouse gas emissions, no long-lived radioactive waste, and no risk of the kind of meltdown that can occur with nuclear fission reactors. The energy density of fusion fuel is so high that a few gallons of water could theoretically provide enough deuterium to meet a single person's lifetime energy needs. Fusion could provide the baseload power needed to support a fully electrified global economy, desalinate seawater at scale to address freshwater shortages, produce green hydrogen via electrolysis for industrial processes and transportation, and power deep space missions that would be impossible with chemical rockets alone. Liquid hydrogen and liquid oxygen have been the propellants of choice for the upper stages of rockets since the dawn of the space age. The space shuttle's main engines burned liquid hydrogen and liquid oxygen, and so does the RS-25 engine that powers the Space Launch System, NASA's new heavy-lift rocket designed for missions to the moon and beyond. Hydrogen's high specific impulse, a measure of how efficiently a rocket engine uses its propellant, makes it ideal for reaching the velocities needed to escape Earth's gravity and travel through the solar system. Stepping back from the technological particulars, there is a deeper philosophical dimension to the hydrogen story that deserves reflection. Why is the universe this way? Why are the fundamental constants of nature set to values that produce a cosmos dominated by hydrogen? A cosmos in which stars burn steadily for billions of years, in which carbon and oxygen and the other building blocks of life are forged in stellar interiors and dispersed by supernovae, in which water has the extraordinary properties that make it the universal solvent of biochemistry, in which DNA can store and transmit information with exquisite fidelity. The fine structure constant, which governs the strength of the electromagnetic interaction, has a value of approximately 1/137. If it were about 4% larger, the triple alpha process inside stars would fail to produce carbon in significant quantities, and carbon-based life would be impossible. If it were significantly smaller, atoms would be larger and less tightly bound, altering chemistry in unpredictable ways. The strong nuclear force coupling constant, which determines how tightly protons and neutrons stick together inside nuclei, is similarly finely tuned. A modest increase would have caused nearly all hydrogen to be consumed during Big Bang nucleosynthesis, leaving a helium-dominated universe with no stellar hydrogen fuel. A modest decrease would have made deuterium unstable, preventing the nucleosynthetic chain from ever getting started. The cosmological constant, which governs the rate of the universe's accelerating expansion, is extraordinarily small, roughly 10 to the minus 122 in natural units. If it were much larger, the universe would have expanded so rapidly that matter could never have clumped together to form galaxies and stars. If it were negative and large, the universe would have collapsed back on itself long ago. In every case, the observed value lies in a narrow range that permits the existence of a complex, structured, life-bearing cosmos. This apparent fine-tuning has generated intense debate among physicists and philosophers. One perspective is the anthropic principle, which comes in weak and strong forms. The weak anthropic principle simply states that we should not be surprised to observe a universe compatible with our existence. Because if the universe were incompatible with observers, there would be no one to observe it. This is logically trivially true, but does not explain why the constants have the values they do. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop at some point in its history. Some physicists find this idea uncomfortably close to teleology, the notion that the universe has a purpose or goal. Others invoke the multiverse hypothesis, which proposes that our universe is just one of an astronomically large, perhaps infinite, number of universes, each with different values of the fundamental constants. In this framework, most universes are sterile, but we inevitably find ourselves in one of the rare universes where the constants are compatible with life, simply because we could not exist anywhere else. Whether the multiverse is a genuine physical reality or merely a philosophical speculation remains an open question, and it may not be answerable by any conceivable experiment. What is not in dispute is that the specific values of the fundamental constants produce a universe that is dominated by hydrogen, and that this dominance is the first and most essential link in the chain of events that leads to stars, planets, chemistry, biology, consciousness, and the fact that you are reading these words right now. There is a sense in which the entire history of the universe is a single story told in the language of hydrogen. The plot begins with the Big Bang, when hydrogen nuclei are forged in the first minutes of cosmic time. It continues through the dark ages, when gravity slowly gathers hydrogen gas into the cradles that will become galaxies. The first climax comes when the first stars ignite, powered by hydrogen fusion, ending the darkness and beginning the long process of element production. Subplots branch off in every direction. The quantum mechanics of the hydrogen atom lays the foundation for all of modern physics. The chemistry of hydrogen bonds makes water liquid and DNA stable and proteins functional. The gravitational dynamics of hydrogen gas sculpt galaxies and spawn planetary systems. The story has a second climax in the present era, as a civilization made of stardust, itself a derivative of hydrogen, reaches out to master the energy of the stars through fusion technology and to build a clean energy economy around hydrogen fuel. And the story has a projected epilogue stretching trillions of years into the future. As the universe continues to expand, galaxies will exhaust their reserves of hydrogen gas. Star formation will decline, and the last stars will eventually burn out. In the far future, the universe may be populated only by white dwarfs, neutron stars, and black holes slowly cooling toward absolute zero. The last faint embers of starlight will die, and the cosmos will enter an era sometimes called the heat death, a state of maximum entropy where nothing interesting ever happens again. Even then, the ghost of hydrogen may linger. Isolated protons drifting through the void, the ultimate remnants of the element that once built everything, may persist for eons beyond imagining. And if some speculative models of physics are correct, protons themselves may eventually decay, with a half-life estimated at greater than 10 to the 34th years, far longer than the current age of the universe. When the last proton decays, the last trace of hydrogen will vanish, and with it, the last echo of the element that wrote the story of the cosmos from beginning to end. But we do not need to look that far ahead to appreciate what hydrogen has given us. Look at the sun rising over the horizon tomorrow morning, and know that its warmth is the product of Hydrogen nuclei fusing in a core heated to 27 million degrees Fahrenheit. Look at the night sky and know that every point of light is a furnace burning hydrogen. Run your hand through water and know that every molecule is held together by hydrogen's covalent bonds and linked to its neighbors by hydrogen's weak but indispensable hydrogen bonds. Think of the DNA coiled inside every cell in your body and know that the double helix is zipped together by hydrogen bonds between base pairs. Consider the carbon atoms in your muscles, the oxygen atoms in your lungs, the iron atoms in your blood, and know that every one of them was forged inside a star that burned hydrogen for fuel. Reflect on the engineers and physicists working right now at facilities across America and around the world, laboring to create a miniature star on Earth, to crack the problem of fusion, to build a future powered by the same element that powers the cosmos. Hydrogen is not just a line on the periodic table. It is not just the lightest atom. It is the origin, the engine, the architect, and potentially the salvation of everything we know. The universe is, in its deepest essence, a hydrogen story, and we are all characters in it.